Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. So today I will continue what we started on the relational algebra, so all the math, and then we'll have a practical part on the queries with SQL, how you can actually apply this relational algebra to real data. That is probably the most useful part for your future projects in like master's thesis, bachelor's thesis, semester projects. Let's get started. So this is where we stopped last time. So remember that we are manipulating relational tables. We are using the set conventions. Every table is a set of records. And we looked at all these pi letters, right? You remember pi, which is the Greek letter. So pi is for projections, right? You specify the columns that you want to include in your output. Then you have sigma, which contains a predicate, and the predicate tells you which rows you want to get. Then we have row, which is to rename columns and to rename tables. And we stopped on the Cartesian product of two tables that basically looks at all possible combinations of one row from the left, R, and one row from the right, S. And so you see there's 2 rows in R, 3 rows in S. So we have 2 times 3, 6 combinations in the Cartesian product. I also explained that when we take the Cartesian product of 2 records, we really flatten everything. So if you take a record with 3 attributes A, B, C, and a record with 2 attributes D and E, and you take the Cartesian product of the two, so the combined tuple, it flattens, and you have a tuple with 5 attributes A, B, C, D, and E. Everybody with me? All right. So now we need to be careful in the case that there is a collision of attributes. So if you now try to do a Cartesian product, but both R and S have the same attribute name, you cannot really build a tuple just by flattening the concatenation of the two, because you would have a problem in the that you would have twice the same attributes. So what you need to do in these cases is to insert a row to rename one of the two B's to an E. So if you have this row B renamed to E in front of S, then you remove that problem, right? And then you make it mathematically consistent again. What happens in real systems is that if you have like this some collision, they will just insert the name of the original table in front of the column. So they would say this is the B coming from R and this is the B coming from S, right? But mathematically, it's not really so nice. Okay, so now that we have the Cartesian product, let's look at the join. The join of 2 tables is actually more practically interesting than the Cartesian product. So the join is, in real life, when you have a database of products, a database of customers, a database of orders, and you want to combine them. But of course, if you have an order, you only want to match the order with the customer that placed this order, right? You don't want the combinations of the order with every customer. And this is called the join. So what happens is that we are going to take these 2 tables R and S that you can see right here, but we notice the 2 columns B, and we are going to match them. It means that this record right here that has B equals 1 will only be matched with this one, and this record right here that has B equals 2 will only be matched with this one, right? So it means that if you look at all possible combinations, only this combination with the 2 matching is interesting to us. And this combination, which corresponds to these 2, is interesting to us. These combinations that would have been part of the Cartesian product, we forget about them, we drop them because they do not match, right? So we only retain these 2, right? And then because anyway, these 2 match, we merge the columns. We just keep B. Who is with me? Right? So again, what happened here is that we took this one and matched it with this one. We took this one and matched it with this one, and we get these 2 records in the results. And now you see the sign is very similar to the Cartesian product, but you add these 2 vertical bars on the 2 sides. So this is called the join, right? It's absolutely fundamental in relational databases. Okay, now, just be careful about the domains. When you have domains, if you try to do a join and the domains are not the same, then that's never going to match, right? Because Booleans are not integers. So in that case, either you can throw an error saying, no, you can only join if the domains match, or so technically, mathematically, it just means you don't define it, it's undefined, or you could define it as empty. You could say that the join of these two is empty and has no record at all because there's never ever a match, right? But this is really a mathematical corner case. Okay. So now the join that I have shown to you here is called a natural join. It's a natural join because we naturally combine the records based on the attributes that they have in common, in that case, B. But what if we have tables that have different attribute names, right? For example, we have ABC and DE. So here we cannot do a natural join because they do not have any attributes in common. But we still want to match, let's say, A with D, right? Let's say we want to match the foo here in A with the 2 here twice, and the bar here with the bar here. It means we need to match A with D. So that's no longer a natural join because the name of the column is not the same. That's called the theta join. And what you do is that it's the same sign, but you add here the criterion for your join. You basically say we want to join these two with the join predicates that A and D must match. Who is with me? Right? This is called the theta join. I don't know why theta, but that's how it's called, right? So basically you take T, you have these 5 columns, and that would be the Cartesian product. But of course, we don't keep them all. We only keep those for which A equals D actually works. So this would be the result of the theta join of R and S with predicate A equals D. Now, could anybody tell me how you could express this theta join using a Cartesian product and sigma, the selection? Yes? Yeah, that's a where. So the where is the sigma, right? The where would be in the sequel, as we will see. But for us, the selection in the math, it's called sigma. So indeed, that would basically the Cartesian product, that would be all combinations, followed by a selection with the criterion. Who agrees with this formula? Right? This is what it is. So what it means is that we have mathematical operations that are fundamental, like the Cartesian product, sigma, and others that can be derived from others. So it means that even if we didn't have the notation with the join on A equals D, it wouldn't be a big deal. We would just use the sigma and the Cartesian product. Okay? So this is getting interesting because now you can do some real math using the formulas, and we'll see you can derive theorems and so on. By the way, since we are at it, you can express the intersection of two sets as two subtractions. Do you know how? If you have, imagine you don't have the intersection operator, that you only have subtraction. Yes? Like this? This is what you hang. Yeah, indeed. So you basically take R minus S, so R when you remove everything from S, and then you do R minus that, right? Who sees it? Do you want a drawing? Let me do a drawing. It's on the blackboard, but I will put it on Zoom later. I'm just doing a Venn diagram, just so you see the visual of that. Or maybe, oh, we might have paper. Oh no, we have paper. It's even better than that. Then I will do it in a way that people will see it on Zoom too. Okay. So basically, we have R and S like this, right? It's a Venn diagram. And the intersection of the two would basically be here, right, in the middle. And so the idea is that this would be R minus S, basically. If you take all the part of R here in the left, but you remove S, that's the part that I have basically grayed here. Who agrees? Yeah. And so now, if I take R minus this, then R is basically the circle that you have here, right? Oh, it's very, very strange to do it in this way, in the mirrored way, but this is R. And if you remove that part, then what you get is the part here. So basically R minus S gives you exactly the intersection, right? Do you see it now? So this is another example of a theorem that you can basically have. Now, turns out you can also express the natural join with a theta join. And the way you do that is you take the Cartesian product, you rename, because remember that the natural join is when there is an attribute that is on both sides. So you rename one of the two attributes on one of the two sides to a different name so that you can take the Cartesian product. Otherwise, you couldn't because of the collision. Then you select based on A equals A2. So A was the A on the left, A2 was the A of the right. And then you take this, and then you project back, because now you have two duplicate columns. So you remove it again, and now you project back to A, B, C, assuming that B and C would be the other attributes in addition to A. Who agrees with this formula? Right? So it basically comes down to saying that a natural join basically means you rename the colliding attributes, then you take the Cartesian product, then you select on the matching, and then you project it back. In fact, the formula you see here is exactly what we had a few slides before when we computed it. See, that's exactly what we did here. Here, we kind of did the rename by giving them different names. So here it would be B, and here it would be B2, let's say. Then the Cartesian product is this. Then the sigma on B equals B2 would select the two green ones. And the projection then would be here, pi ABCD gives you that, right? So this animation here is exactly the same as the formula that is right here. That corresponds exactly to the slides, except that it was B instead of A, and it was projected to ABCD, okay? So you can have theorems like that. And what becomes really, really nice is that you can have exercises on that, but there's many, many, many little things that you can start proving. For example, you can prove that selections commute with one another. If you take a table and apply a sigma with a predicate, and then apply another sigma with a different predicate, you can swap the sigmas. You can apply them one before the other, it doesn't matter. So this says that it's commutative. Just like addition is commutative, A plus B is the same as B plus A. Selections commute with projections. So you can swap pi of sigma of R is the same as sigma of pi of R. Basically, you can swap them. There's just a little fine-grained comment here, is that it only commutes if it makes sense. Because if the projection removes a column that is used in the sigma predicates, then of course it wouldn't make sense. If you project first and then you apply sigma, but it doesn't see all of the attributes that the predicate uses, then that doesn't work. So they commute with projections to the extent that it makes sense. Then projections commute with one another. It means that if you take a table and let's say you project and then you project again, they commute. This one requires a bit of fine-tuning and allowing the definition of projections where you have columns that don't exist, right? So this is a bit subtle mathematically. Then we have joins that are commutative. Union is also commutative. Intersection is also commutative. So for the join, for example, it means that A joined with B is the same as B joined with A, right? R joined with S is the same as S joined with R. The order of the tables doesn't matter. Then we have yet another one. It's that join, union, and intersections are associative. It means that if you take three tables and you try to do R joint S joint T, it's the same as R joint S joint T, right? If you can join 10 tables, it doesn't matter how you compute the joins, in which order you compute the joins, right? So it is associative. Then we have projection distributing over union. Distributive, if you've never heard of it, it's the case with multiplication and addition. It's basically saying that C times A plus B is the same as C times A plus C times B, right? It means that multiplication projects over addition. The same goes with projection distributing over union. What it means is that if you project the union of R and S, it's the same as taking the union of the projection of R and the projection of S, right? You can first either do the union, then the projection, or first do the projection on both and then take the union. That's what it means, but it doesn't distribute over intersection and subtraction. That's a good exercise to find counterexamples of that. Then selection distributes over union, intersection, and subtraction. So it means that the selection of the union of two tables is the same as the union of the selections. You can also swap them. Joins distribute over union. So it means that the joins of a table with the union of two tables is the same as the union of the join of the first table with one of the two and the first table with with the other one. Okay, so you basically can derive all theorems, and then you can also say that a projection is absorbed by a projection on a smaller subset. What it means is that if you take the projection on ABC and it's followed by the projection on just A, then you can just directly project on just A. You don't need the intermediate projection to ABC. So it's absorbed, just like we say that 0 is an absorbing element in multiplication, because anything times 0 is 0. Okay. So this is just the sort of things you will have, I think, some exercises on this. But what that tells us is that even though we started with something relatively simple, with just a table that has rows and columns, we were able to build a whole algebra on top of it with sigma, with pi, with rho, with Cartesian product, with union, intersection, subtraction, with join, and so on. So it's extremely powerful mathematically. And so this is just some of the theorems that you have, but there's a lot out there. So you see, it's really funny because we did the same thing as can be done with numbers, but we did it with tables. All these kind of things. Okay. Shall we go to the next operator? Yeah. So this is grouping. This one is in analytics is absolutely fundamental. So grouping means that you have a table like this that has two columns. That's fake data here. But you see that the values in G, they can repeat. You have foo, you have bar, and you have foo bar, right? So three different values. What we'd like to do is some aggregation. We'd like to aggregate everything, all the values, all the integers associated with foo, all the values associated with bar, and all the values associated with foo bar. That's called an aggregation. So what's actually going to happen is that first, we need to put them together. So here I just shuffled around by putting the foos with the foos, the bars with the bars, and the foo bars with the foo bars. Just shuffled a bit. And then we kind of merge the group like this, right? Noticing it's the same. And then I can aggregate, for example, with a sum. So I could do 19 plus 4 plus 46. And this is what it gives to me. What you see here is a grouping, an aggregation, right? So this is the original table, and we group on G, doing a sum on A, and we obtain this. For whom does that make sense? Right? Okay, this is a group by. Okay, what you see in the middle is only a visual of what happens, right? But this is really the input, and this is the output. Looks like I'm done talking, really? Oh yeah, just because my hand was raised, I guess. Okay, it's this AI stuff that interferes. All right, so now I did the example with a sum, but there's many others. You can also count. For example, imagine you have all these values in a group, you could count them, that's 11. You could take the sum, that's 55. You could take the average, that's just a 5. You could take the mean, which is 0. You could take the max, which is 10. So we have plenty of different aggregation functions that we can use. The mode, do you know what the mode is in statistics? That's the values that is the most frequent. So here I doubled the 7, for example, and here the mode would be 7. Right? And the variance, so there's many, many different things that you can do. So basically, you can classify the aggregation functions based on the domains. For example, if you want to do the sum of the numbers in the same group or the average or the variance, you need to have numbers because you need to be able to sum over them and to divide for the average, right? So that only works with integers, doubles, you know, all the numeric values. For the min and the max, you don't necessarily need numbers. You just need something that can be compared, smaller than, greater than. You just want the highest and the lowest. Do you see that min and max would also work with dates, for example? If I have dates, I can take the latest date or the earliest date. I cannot sum dates, right? So the sum of dates wouldn't make any sense, but the mean of dates or the max of dates would make sense. So min and max are a bit more lenient in the requirements. You can do it with more kinds of domains. So you just need to be able to compare them. So dates times works as well. Of course, you can do it with numbers too, but also on dates. And mode is even more powerful because that works just with the equality. You just need to compare if it's equal or not equal because you just want the most frequent number of occurrences, right? So here, that's called categorical. You just, it could be with strings, for example, or labels in machine learning. Okay? So this is the kind of aggregations. If you just want to learn 5 of them, then learn count, sum, average, mean, max. These are the core 5 aggregations that you need to know. Count, sum, average, mean, max. Right? Okay. So we have a letter for that in Greek, and that letter is gamma. So here's an example. Gamma is a bit more complicated to use than sigma or pi or the others, but I'll explain that. So let me take this, this table. So here, I would like to group based on cities and countries, right? So I want to match these two, Switzerland, Zurich, Germany, Berlin, and Germany, Frankfurt. So I have 3 groups, right? And what I want to do here, I would like to sum on the price. So for this column, I want to sum this and this, to sum this and this. And here I want to count. I don't want to do the sum, I want to count. So here that's 2 of them, and 1 of them, okay? So the way I write it down in the formula is like this. So I have gamma with a huge thing here of transaction. Transaction is just the name of the table. So what goes in here? First, the columns that I want to group on. These are called grouping keys. So just country, comma, city, right? These are my grouping keys, right? For the other columns that I don't group on, I can specify aggregates, aggregation functions. So for price, I'm saying that the sum of the price will give me a column called volume, and the count of the customer will give me a column called num transactions. What I get out of that, mathematically, out of this gamma call, is this. So I have again country and city, but now you see there's no longer any duplicates. There's just unique combinations here, 3 of them. And now I have my 2 aggregated columns that I specified here, where volume is the sum of the price. So you can check that this is this plus this. This here is this plus this, and this is this, right? And the count is 2, 2, and 1, right? So 2, 2, and 1. Who is with me? Who is not with me? Okay, so you all are. So this is the gamma. Okay. So what is very important here, because it's easy to get things wrong, there's a few golden rules that you should follow to not mix things up. So the first thing is that you really need to cleanly separate between the columns that you group on and the columns that you aggregate on, right? So every column either is a grouping key, then you just put it like this, country, city, without anything else. Either it's a grouping key, or you aggregate on it, or you don't use it at all. You can also just completely ignore a column. Then you don't do anything with it, and it doesn't appear in the outputs. So here, country and city are grouping keys. Price and customer are aggregated on. Okay. Never mix things. Do not say group on country and then count of country. Do not do that sort of things. Do not mix the columns on both sides. Either you group or you aggregate or you do nothing for every column. Okay, so grouping is basically visually, this is what it's doing, right? You just to put together the tuples that have the same value for the grouping keys, and then you compute some aggregations. Okay? So I've showed you the selection, the projection, the renaming, union, intersection, subtraction, Cartesian product, join, grouping with gamma. So that's a lot of things that you can do, right? And then we'll see how we do it with SQL, of course, but this is the math. Now, what I've shown to you is sets of maps. I've shown to you how it works if we assume that there is no order in the table and there is no repetition. What if we want to extend the semantics of all of these operations to bags of maps? It means that we would allow for the repetition of values. Well, it can be done. It's actually easier than you think. So, for example, that would be a set of records because we don't allow duplicates. That would be a bag of records because you can see, for example, foo bar for true appears multiple times, right? So this is a bag of records. Now, turns out you can also define the union of a bag of records. Can anybody tell me if I take the union of these two and I have the tuple bar2 false, that appears twice in R and once in S. If I do the union, how many times will it appear in R union S? Anybody? 3, right? If I take the union, I just add them. So if I have m times a tuple in R and n times a tuple in S, then it will appear m plus n times in T. Who agrees? Right? Okay. What about the intersection? You have m occurrences of R and you have n occurrences in S. How many occurrences will there be in the intersection? Yes? The smaller the one, right? So indeed, the minimum of m and n, right? So that's what we do. So you see, it's slightly more involved than just taking if it's on set. You just need, now you need to count. So the union is the sum, and for the intersection, we take the minimum number of times, okay? And then for the subtraction, this one is a bit more involved, but the subtraction, it's this more complicated formula that it's the max of 0 or n minus n. What it really means is that it's basically m minus n. So you need to, it's a subtraction, right? So m minus n. But if it's negative, you cannot have a negative number of occurrences. So this is why there's the max with 0. It basically says if n is smaller than n, that's just going to be 0. You don't go negative. Okay. So basically, we can do it. We can generalize union, intersection, and subtraction to bags. What about projection? Well, that's easy too, right? It's relatively natural to do. You just project every one of the records, you project it to the columns that you want. Since it's bags, you don't even care about eliminating duplicates. So the difference when you do it on a piece of paper is that if you do a projection on sets of maps, you need to eliminate duplicates. But if you do a projection on bags of maps, you don't care about duplicates. All you do is remove the column and that's it, right? So it's actually easier to do. What about the selection? This one is easy too. You just, it's a bag of maps. You just throw away anything that doesn't meet the selection criterion. You throw it away. And you also don't need to worry about the duplicates. Okay, so pi and sigma are really straightforward on maps. Renaming is straightforward too. You just change the name of the column, so the semantics is exactly the same one as it was on sets of maps. Renaming the table, that's the same, nothing changes. So you see it's pretty straightforward. With the Cartesian product, here you just need to think a little bit. When you look at all possible combinations of one tuple in R and one tuple in S, let's say I have a tuple that occurs R times in R and another tuple that occurs S times in S. How many times will I include the combination of the two in my outputs with the Cartesian product? R times S, exactly. So I just multiply the two. So if I had it twice on the first time on R and 4 times in S, that would be 8 in the outputs, okay? So this is R times S. Okay. And now I have something new that I didn't have on sets. It's delta. Delta is yet another Greek letter. Delta means you eliminate the duplicates. So if you take delta of R, that basically means that the duplicate goes away, right? And it turns out that now you have sets of maps because it's basically a bag of map, but the occurrence is at most 1. But a set is also a bag, right? So this works, okay? So again, we can have sets of maps, bags of maps, lists of maps. I'm not showing for lists, but you can do the same. You can also extend the semantics of all the Greek operators to lists of records. Okay. One more thing that you have for lists is sorting. You also have an operator where you specify the columns to sort, and it's going to shuffle the records to put them in the right order. Now, when you sort, I'm sure you already did that in Excel or in some spreadsheet software, right? You can sort on multiple columns, and for every column, you need to say it's ascending or it's descending, right? And then you can have you have an order in the columns in which you sort. You have the primary column, you have a secondary column in case of equality of the first, and so on. Okay. So this is the math. I'm done with the relational algebra, right? So it's a bit heavy because that's also quite theoretical. But this is the reason I alternate between theoretical and practical, because now we are going to get back to a practical session with SQL, and that should we should land back on Earth now. Do you have any questions on the relational algebra? No questions? Do we have questions on Zoom? No questions on Zoom? Okay. So I'm going to stop here, and we are going to go to the next one.